Hello everybody, my name's Rod Burns. I work at a company called Codeplay Software. I'm pleased to introduce you to this SYCL tutorial as part of IWOCL and SYCLcon. Tutorial has contributions from all the implementers of SYCL, including Intel, SYCL and Xilinx. If you have any questions, ask them on the Slack channel, and at the end of the presentation, the first presentation, there'll be a link for you to do the code exercises. So I'll start off with the first presentation.
Hi everyone, my name is Gordon Brown and I'm going to be presenting this Introduction to SYCL tutorial. I'm a Principal Software Engineer at Codeplay Software, where I'm the technical lead on the Compute CPU runtime and a contributor to the SYCL working group in Kronos. This tutorial is split up into 4 parts. Firstly, there is an introduction to SYCL, where I will cover the broad strokes of the programming model. Then we'll move on to topology discovery and queue configuration, where I'll cover how to discover what devices are available in your system and how to create a queue in order to start queuing work to it. After that, I will cover how to define kernel functions, the actual functions that will be compiled and run on your device. And then finally, I will cover how to manage data in SYCL using buffers and accessors. After each of these lectures, there will be an opportunity to ask questions, and then there will be a hands-on exercise to try out what you've learned. Experts from all 4 of the implementations of SYCL are also available on Slack throughout this tutorial to answer any questions and provide support. So let's get started with the introduction to SYCL. In this lecture, we're going to cover what the SYCL 1.1 specification is and what implementations there are, what the major features of SYCL are, what the components of a SYCL implementation are and what they do, the anatomy of a typical SYCL application, and finally where to find useful resources both for during this tutorial and for after if you wish to continue diving deeper into learning about SYCL. So first and foremost, what is SYCL? So SYCL can be described as a single source, high-level, standard C++ programming model that can target a wide range of heterogeneous platforms. Now that's quite a mouthful, so let's break that down and see what it all means. Firstly, SYCL is single source. What this means is unlike traditional C++ applications which have a single compilation path of a source file compiled into an object and then linked to create an executable, SYCL applications have 2 compilation phases, one for the host compiler and one for the device compiler. Unlike traditional heterogeneous programming models like OpenCL, which have 2 separate sources, one for the host application and one for the device code, SYCL has a single source file, containing both the host application code and the device code, all in C++. So how does this work? Applications in SYCL are written against a single SYCL API, and both the host and device compilers parse the same API, but they interpret it differently. First, the device compiler compiles the SYCL application and pulls out specific parts to compile SYCL kernel functions, generating some form of binary. This is often a standard IR such as Spear or SpearV, but it can also be a proprietary IR such as PTX or even an ISA for a specific architecture. Then the host compiler compiles the same SYCL application but outputs a standard CPU binary, which will run on top of a SYCL runtime in queuing to OpenCL, or in some cases another backend. This is then linked with the binary generated by the device compiler to create a single executable that has both the host application code and the device code embedded inside. The one thing to note here is that there is always 2 compiler passes as I've described, but sometimes this is done by a single compiler driver. Next, SYCL is a high-level programming model. This means SYCL provides a number of high-level abstractions over common boilerplate code in OpenCL and other backends. This includes things like selecting devices, allocating and copying data, managing dependencies, scheduling, compiling kernels, and much more. To demonstrate this, here we have a comparison of equivalent applications in OpenCL in blue and one in SYCL in orange. One of the key goals of SYCL is to make simple things simple, make the most common behavior the default, but still provide access to more complex solutions if you need it. SYCL is also standard C++, which means unlike many other programming models and languages which require language extensions, pragmas, or keywords, SYCL doesn't require any of that. It's pure standard C++. This means that any SYCL application will compile and run using a SYCL library, even if there's no device compiler and no devices available in your system. In fact, this is a feature of SYCL. It's called the host device, and it's used for debugging kernel functions. Finally, SYCL targets a wide range of heterogeneous platforms. SYCL is designed to be able to target more devices than any other programming model. SYCL can target any device supported by its backend, and SYCL can target any number of backends. Now, the current SYCL 1.2.1 is tied to OpenCL as a backend, so while implementations such as HipSYCL and DPC++ support HIP and CUDA backends, they cannot be fully conformant. However, as you will see in another presentation that I'm giving in IWOCL this year, SYCL 2020 more than meets the eye, SYCL 2020 is changing that. So what implementations are there, and which one is best for you? Firstly, there's DPC++, which is an open source implementation led by Intel as part of their One API solution, and is intended to be merged upstream to Clang and LLVM. DPC++ supports OpenCL and now CUDA backends through its plugin API. Between these two backends, DPC++ supports Intel CPUs, GPUs, and FPGAs, as well as NVIDIA GPUs. Next we have Compute CPP, a commercial implementation developed by Codeplay and optimized for embedded, mobile, and automotive architectures. Compute CPP supports Intel CPUs and GPUs, ARM Mali GPUs, the Renesas RCAR platforms, and experimental support for NVIDIA GPUs. Next up we have SYCL, which is an open source project led by Renan Kerial at Xilinx. SYCL supports any CPU through OpenMP and TBB, and also has experimental support for Xilinx FPGAs. Next again we have HipSYCL, which is another open source project led by Axel Alpe at the Heidelberg University. HipSYCL runs on top of ROCm and CUDA backends to provide support for AMD and NVIDIA GPUs, as well as support for any CPU via OpenMP. Finally, we have SYCL GTX, which is an early prototype implementation developed by Peter Zuzik, who is now at Codeplay. SYCL GTX is now largely used for experimenting with new features. So there are now many SYCL implementations to choose from, depending on which platform you're using. Many of these implementations also have their own extensions, so it's always worth checking these out, as many of these can be early indicators of what is to come in future revisions of the standard. For the hands-on exercises in this tutorial, we will provide instructions for how to use Compute CPP, DPC++, and HipSYCL. Next, we're going to look at what is in a SYCL implementation. First, every SYCL implementation must provide the standard SYCL API. This is a standard C++ template library that provides the features developers need to write SYCL applications. This same API is used for both host application code and device code. Next up is the SYCL runtime. This sits below the SYCL API and performs a number of functions. It loads and compiles kernels, it performs data dependency analysis, and it schedules all operations required to manage data and enqueue kernels to the backend. Next is the host device. The host device is an emulated SYCL device which guarantees the same execution and memory model as a regular SYCL device, but runs natively in the SYCL runtime. The host device can be used as a fallback and to debug kernel functions. Next up we have the backend API, such as OpenCL, that sits underneath the runtime and performs any commands enqueued to it for a particular device. The standard backend for SYCL 1.2.1 is OpenCL, but some implementations, as we've seen, support other backends. Finally, we have the device compiler. The SYCL device compiler is a standard C++ compiler which can parse and compile SYCL kernel functions and integrate with the SYCL runtime. The SYCL device compiler will output kernels in some binary format that can be consumed by a backend. This is often a standard IR such as Spear or SpearV, but can also be a proprietary IR like PTX or an ISA for a particular architecture. Now we're going to look at what a typical SYCL application looks like. For this, we're going to look at how to create a simple vector add application. Now we're only going to touch on these concepts to give you an idea of how everything fits together, because we're going to dive much more further into these in later lectures. The first thing to do, like any library, is to include the header file. For SYCL, this is SYCL.hpp. SYCL.hpp includes the entire SYCL API, so that's everything you need to develop a SYCL application. We also import the CL-SYCL namespace here to reduce the verbosity for the slide code. Now that we've included the header file, the first thing we need to do is create a queue to enqueue work to. One of the simplest ways to do this is to construct a queue object, initializing it with a device selector. A device selector is a function object which describes a heuristic for scoring devices. When you pass a device selector to the queue constructor, it will look at all the devices available in the system, score them all according to this heuristic, and choose the one with the highest score. In this case, we're using the GPU selector, which is one of the standard selectors provided with the SYCL API, which will only choose GPU devices. You can also construct a default queue, which will use the default selector to choose a device. The default selector is another standard selector, but its heuristic is implementation defined. Next, we have to create a command group. In SYCL, a command group represents a single unit of work that is enqueued to a queue to be scheduled. A command group represents a command such as a kernel function, often an ND range, and accessors which describe the dependencies. To create a command group, you call the submit member function on the queue. This function takes a callable, which itself takes a reference to a handler object. This function acts as a factory for constructing a command group by associating dependencies through accessors and a command, such as a kernel function, with the handler object. Now we initialize some vectors for our inputs and outputs. Then we create a buffer for each of these input and the output to manage the data across the host application and the device that we want to enqueue a kernel function to. To create the buffers, we specify an element type, dimensionality, in this case float and 1, and initialize them with a pointer to the data and a range describing the number of elements. Buffers synchronize and copy back to the original pointer on destruction. So adding this scope triggers this synchronization and copies the result back to the output vector when this scope is left. Now we create accessors for each of these buffers to describe the data dependencies for the command group. To do this, we call getAccess on the buffer objects providing the handler to create the association between the accessors and the command group. For the two input accessors, we specify the access mode read. This tells the command group that we are only reading from the input buffers and it should not copy back to them. For the output accessors, we specify the access mode write. This tells the command group that we are writing to it and it should copy back. Next, we define the kernel function itself. To do this, we call the parallel for member function on the handler object. We pass this a range to describe the range to invoke the kernel function over, and a lambda representing the kernel function itself, which takes an ID representing the current iteration. The kernel function performs a single vector add operation, reading and writing from the accessors, passing in the ID to the accessor subscript operators. This completes the application. If you were to compile and run this with proper initialized inputs, it would enqueue a kernel on the GPU and return the result to the output vector. You'll probably notice though that the parallel for function also takes a template parameter. This is used to name the lambda. Since C++ does not have a standard API for lambdas, this is required to allow the host and device compilers to communicate. SYCL kernel names also follow C++ ODR rules, so if your kernel is defined in a template context, the name too must be templated. Finally, one other thing to add, and an important one. The SYCL runtime manages errors by throwing exceptions. Some of these are thrown synchronously, and some of them are thrown asynchronously. In order to catch these, you must wrap the SYCL application code in a try-catch block and provide an async handler to the queue. But I will explain more about this in this next lecture. So where to get started with SYCL? Firstly, you can visit the Kronos website to get the latest revisions of the specification. You can also check out the documentation provided one of the SYCL implementations that I described. Or you can also check out the SYCL.tech website, which provides news updates and blog posts about all things SYCL. This concludes the lecture on an introduction to SYCL. There should now be some time for us to answer any questions you have on this.
Thank you to Gordon for that. There's a link on the screen which you can follow to find the exercise materials, and if you've got any questions about any of the content that was presented there, then put them on the Slack channel and Gordon and others will be there to answer those.
Welcome back. In this lecture we're going to be looking at the SYCL system topology and how to create a queue so you can start submitting work to a device. Welcome back. In this lecture we're going to be looking at the SYCL system topology and how to create a queue so you can start submitting work to a device. In this lecture we're going to cover the SYCL system topology and how to traverse it, how to query information about a platform or a device within the topology, how to select a device both manually and using device selectors, how to configure a queue, and then finally the SYCL scheduler and how to submit work. First of all, let's take a look at the SYCL system topology and how it's structured. A SYCL application can execute work across a range of different heterogeneous devices, and the devices that are available in any given system are determined at runtime when you do topology discovery. When querying the topology of a SYCL system, there will be a number of platforms available. Each platform is an implementation of a particular backend. For example, an OpenCL backend for Intel and an OpenCL backend for NVIDIA are different platforms. This is an important distinction because platforms can generally not communicate directly with each other, and we'll see this come up in a later lecture when we cover data movement. Each platform will also have a number of devices associated with it. These can be CPUs, GPUs, FPGAs, or any other kind of accelerator. In SYCL there is also a host device, which executes SYCL kernel functions natively within the SYCL runtime. The host device emulates the execution model and memory model of a regular SYCL device. This can be very useful for debugging SYCL applications, as some devices may not have native debugging tools available. There is always one host device. Each SYCL implementation must have one, and there can only be one. The host device is also associated with the host platform, and again there can only ever be one host platform. Platforms and devices are represented by the platform and device classes respectively. A default constructed platform object creates a host platform, and a default constructed device object creates a host device. Now there are two ways in SYCL to traverse the topology of a system. Firstly, there are APIs which allow you to manually query the available platforms and devices. Secondly, there's a mechanism called device selectors for automatically traversing the system and producing a device based on a heuristic for scoring devices. First, we're going to take a look at how you would manually traverse the topology of a system. The platform class provides a static member function called getPlatforms. This returns a vector of all the platforms available in the system, including the host platform. So in this example, where we have two OpenCL platforms and a host platform, getPlatforms would return all three of these. The platform class also provides a member function called getDevices. This returns a vector of all the devices associated with a specific platform, including the host device. So in this example, where the Intel OpenCL platform has a CPU device and a GPU device, if you were to call getDevices on the Intel OpenCL platform, it would return both of these devices. Alternatively, the device class also provides a static member function called getDevices. This returns a vector of all the devices available in the system for all platforms. Again, this includes the host device. So in this example, where we have 4 devices across our 3 platforms, getDevices would return all 4 of these. Next, we're going to look at how to traverse the topology using device selectors. To simplify the process of traversing the topology and selecting a device, SYCL provides the device selector mechanism. A device selector is a function object which inherits from the device selector class. A device selector provides a heuristic for scoring devices. SYCL provides a number of standard device selectors, but users can also create their own custom ones. The device selector class provides the member function selectDevice, which will traverse the topology for every available device, pass each of them through the device selector, obtaining a score for each, and then it will choose the device with the highest score. Any device with a negative score will never be chosen. Here we have an example of constructing a device selector and calling the selectDevice function to retrieve the resulting device object. The default selector is one of the standard device selector types provided by SYCL. The default selector will choose a device based on an implementation-defined heuristic, so the device that is chosen by this can vary from one implementation to another. Okay, so now that we know what a device selector is, how do we create one of our own? So it's actually pretty straightforward. A device selector must inherit from the device selector class, and a device selector must provide a function call operator which takes a reference to a device object and returns an integer. The body of that function call operator is the logic which defines the heuristic of your device selector. This is how you define how each device is scored, and the value returned is the score for the device that is passed in. In this example, we return a positive score for each GPU device and a negative score for everything else. However, this logic could be much more complex, querying the vendor or the capabilities of the device. If you end up with more than one device with the same score, then the one that is chosen is implementation defined. Now that we have our device selector, to use it we can simply pass it to the constructor of the queue, and this will create a queue which will enqueue with the resulting device. There are a number of other ways to configure a queue, and we'll touch on some of these later in this lecture, but this is the most common. Now we've covered how to create a device selector, but how do you decide what to score each device? So in the body of your device selector's function call operator, you can query the device or its platform for information about it to determine its score, depending on the heuristic that you want to define. You can do this by calling the getInfo member function template, providing one of the many enum values corresponding to different pieces of information that you can query. You can retrieve the platform associated with any device by calling the getPlatformMember function. Here we show some of the information that you can query, but for a full list of these queries you should see the SYCL 1.2.1 specification or reference cards. So now we're going to take a look at what a queue is and what it does. But first, before going into what a queue is, it's first important to understand what a context is. A context in SYCL is an object which manages the underlying resources of a platform and a number of devices. A context can represent one or more devices, but they must all be associated with the same platform. So in this example, we've created a context for the Intel OpenCL platform and both its devices. Now a queue in SYCL is the object which is used to submit work. There are many ways to configure a queue in a SYCL application, from the very simple to the more complex, but every application must have one. A queue's job is to process command groups and submit commands to the scheduler for a particular context and device. A SYCL application will often want to target multiple devices. This can be useful for task-level parallelism and load balancing. Here we have two queues, one for the CPU and one for the GPU, both associated with the same context. This is important for being able to communicate efficiently between the two devices. So how do you create a queue? There are a number of ways to do this, some involving more complex configurations of contexts, but in this lecture we're just going to focus on the most common. The simplest way is to default construct a queue, which will use the default selector. This will create a queue which is associated with the device that is selected by the default selector and will implicitly create a context for it and all other devices associated with the same platform. So in this example, if we assume that the default selector chooses the Intel GPU device, then we will create a queue for the Intel OpenCL GPU which has an implicit context which is associated with that device and the Intel OpenCL CPU as well. Next, as we've seen in earlier examples, you can construct a queue from a device selector. This will create a queue which is associated with a device that is chosen by that device selector and implicitly create a context, just as before. So in this example, we end up with the same result, but here we explicitly request an Intel GPU. So now that we have a queue, how do we submit work to it? In SYCL, all work is submitted to a queue. This is done by using the submit member function. This will process a command group and submit commands to the SYCL scheduler for the context and device associated with that queue. So here we submit a command group to the GPU queue, where it is then processed and submitted to the scheduler. Then once the scheduler decides to execute those commands, they are then enqueued to the target device. The same scheduler is used for all queues in order to share dependency information and maintain a single ordering of commands. So in this case, where we have two command groups submitted to different queues, each queue will process their respective command groups and submit them to the scheduler. The scheduler will then decide the ordering of the commands in each command group based on the dependencies of each, and then enqueue the commands to the target devices in that order. The submit member function takes a callable, which can be either a function object or a lambda expression. the callable must take as its parameter a reference to a handler object. The handler is created by the SYCL runtime and passed into the callable by the submit member function, so you cannot manually create a handler. The body of the callable represents the command group scope. This is where you construct a command group. And you do this by associating dependencies and commands with the handler object, but we'll cover this in more detail in later lectures. The command group scope is called exactly once, and when this function returns, the submit member function will then construct a command group. This command group is then processed and submitted to the scheduler, where its commands are enqueued asynchronously. A queue object will not automatically wait for submitted work to complete when it's destroyed. There are other ways to wait for work to complete if you have data dependencies, and we will cover this in a later lecture, but it can also be useful to explicitly wait on the queue to complete any outstanding work. You can do this by calling the queue's wait member function. Okay, now that we have covered how to submit work to a queue, it's important to now understand how to handle any errors that might occur. In SYCL, errors are handled by throwing exceptions, and it's crucial that these errors are handled, as otherwise your application may fail silently. In SYCL, there are two main kinds of errors: synchronous errors, which are thrown directly to the user thread, and asynchronous errors, which are thrown by the SYCL runtime. Here is a diagram to help illustrate this. Any error which occurs within the SYCL interface will generate a synchronous error. However, any error which occurs after a command group has been submitted will generate an asynchronous error within the SYCL runtime. This is because once a command group is submitted, any error which occur may happen in another thread. Here we have the vector add example from the last lecture. In this version, we don't have any error handling, which means if an error does occur, the application will fail silently, except perhaps a log to the console, but that's implementation defined. The first thing to do to handle errors is to wrap any SYCL application code in a try-catch block. This will catch any synchronous exceptions being thrown by the SYCL API. Next, you must provide what is referred to as an async handler. An async handler is a callable, so a function object or lambda expression which can receive asynchronous exceptions. This happens when you either call one of the queue's member functions throw asynchronous or wait and throw. The reason for having an async handler is that when an exception is thrown by the SYCL runtime, this is often in another thread, which means there's no way to communicate this to the user thread. So having a callable which can handle asynchronous exceptions invoked when the user calls one of the above functions, these exceptions can then be processed and potentially rethrown into the user thread. An async handler must take as a parameter an exception list. The exception list is a wrapper around a list of exception pointers, which can be iterated over. Exception pointers can then be rethrown by calling std rethrow exception. Once an exception, synchronous or asynchronous, is caught, it can then be used to provide information about the error. The what member function, just like for any exception, will provide a message with more details about the error that occurred, though the exact details of that message is implementation defined. If the exception has an OpenCL error code associated with it, this can also be retrieved by calling the getCLcode member function. If there is no OpenCL error code, then this will return CL success. Most exceptions will also have a context associated with them. The hasContext member function will tell you whether there is a context associated with the error. Then, if this returns true, you can call the getContext member function to retrieve that context. Finally, we're going to take a look at how to debug SYCL kernel functions. As mentioned before, every SYCL implementation must provide a host device. This means that SYCL kernel functions can be debugged using a standard C++ debugger, such as GDB, LLDB, or Visual Studio. To do this, you simply use the host selector when creating your queue, and kernel functions will run on the host device. It's as simple as that. So this concludes the lecture on SYCL topology and creating queues. There should now be some time for us to answer any questions that you have on this.
Welcome back. In this lecture we're going to be looking at SYCL kernel functions, which represent the actual functions which are going to be compiled and invoked on your chosen SYCL device. But as a precursor to this, we're also going to be looking at the SYCL execution model and the ways in which it allows you to express parallelism in your applications. In this lecture we're going to cover the SYCL execution model, the SMT model for describing parallelism, how to define and invoke a SYCL kernel function, the rules and restrictions which apply to kernel functions, so you know what you can and can't use in a kernel, how to use both lambdas and function objects to define your kernels, and then finally we're going to cover how to manually compile a kernel function to give you a bit more control over how it's compiled. So we're going to start with the SYCL execution model. In SYCL, kernel functions are invoked on what are referred to as work items. You can think of a work item as a thread of execution. It will execute a kernel function from start to end. A work item can run on a CPU thread, a SIMD lane, a GPU thread, or any other kind of processing element. This depends on the kind of SYCL device that you're targeting. SYCL kernel functions are generally invoked on a number of work items in parallel, and these work items are grouped together into what is referred to as workgroups. The size of the workgroups is generally relative to what is optimal for the device that you're targeting, but can also be affected by the resources used by each work item. Choosing the best workgroup size is often a key optimization for SYCL applications, as it ensures optimal occupancy on the target device. The full iteration space that a SYCL kernel function is invoked over is described by what is referred to as an ND range, which means n-dimensional range. An ND range contains a number of workgroups, and each of those subsequently contains a number of work items. And the workgroups are always the same size, they always have the same number of work items each. An ND range describes a multidimensional iteration space, effectively how work items and workgroups are composed. An ND range can be 1, 2, or 3-dimensional. Here we have an example of a 2-dimensional ND range. An ND range has two main components to it. Firstly, there's the global range, which describes the total number of work items in each dimension. In this example, the global range is 12 by 12, so 12 work items in each dimension. Then there's the local range, which describes the number of work items per workgroup in each dimension. In this example, the local range is 4 by 4, so 4 work items in each dimension. So this gives us a total iteration space of 12 by 12 work items that's then equally subdivided into 4 by 4 workgroups. The global range must always be equally subdivisable by the local range.
When you enqueue a kernel function over an ND range, that function will be invoked exactly once per work item in the iteration space. Each invocation of the kernel function knows which work item it is on and can query information about its position in the ND range iteration space. Each work item has the following knowledge about its position in the ND range. Here we have an example to demonstrate this. First we have the global range. This is the total number of work items in the ND range in each dimension, in this case 12 by 12. Next we have the global ID. This is the index within the global range of the current work item, in this case the index 65, which is highlighted here in orange. Next we have the group range. This is the total number of work groups in the ND range in each dimension. In this case this is 3 by 3, as the ND range divides up evenly into 3 by 3 work groups. And the group ID, similarly, this is the index within the group range. In this case the index 1, 1, highlighted here in yellow. Finally we have the local range, which is the total number of work items per work group, in this case 4 by 4, and the local ID, which is the index within the local range of the current work item, in this case 2, 1, which is highlighted here in orange relative to its work group, highlighted in yellow. One thing to note here is that different levels of this information will be provided to the kernel function depending on which API you use to enqueue your ND range. But we'll be covering these different APIs later on in this lecture. Typically, an ND range will be invoked over a very large number of work items. This can often be in the thousands. Multiple work items in an ND range will generally execute concurrently at any one time, and on vector hardware such as SIMD CPUs and GPUs, this is often in lockstep, which means single instructions spread across a number of work items. The number of work items that execute concurrently will vary from one device to another, and this can also vary depending on the resources used by each work item for the particular kernel. However, work items will be batched with other work items in the same workgroup, allowing for synchronization within a workgroup. But the order in which work items and workgroups are executed is implementation defined. The work items of a workgroup can be synchronized using a workgroup barrier. When triggered, a workgroup barrier will wait for all other work items in the same workgroup to reach that point before any of those work items are allowed to continue on. SYCL doesn't, however, support synchronization across all work items in an ND range. This means that workgroup barriers will not prevent adjacent work items in a different workgroup from progressing. The only way to achieve this is to split the computation into separate kernel functions and enqueue separate ND ranges. This is important to remember when sharing data between work items. Now we're going to take a look at the SIMT programming model and what that means for how kernel functions are described in SYCL. So SIMT stands for Single Instruction Multiple Thread, and this is a paradigm that is used for expressing parallelism. To demonstrate this, let's look at two examples. In the first example on the left, we have a regular sequential CPU code. We have a function which takes an input pointer and an output pointer and loops over the pointers to compute some computation for 1024 iterations. In this case, the function describes exactly how the iteration space is traversed. In the example on the right, we have a function which takes again an input pointer and an output pointer, but also takes an index, and this function computes just the iteration for that specific index. We then invoke that function again for 1024 iterations, but this time by calling parallel for. Now in this example, the function describes only a single iteration, and the parallel for manages how the iteration space is traversed, allowing it to parallelize the computation. And this is how SYCL kernel functions are described, by defining a single iteration, which is then invoked for each iteration of an ND range. Now we're going to take a look at the different ways in which you can define a kernel function and enqueue an ND range in SYCL. SYCL kernel functions are defined and enqueued over an ND range by calling one of the various APIs. These are provided by the handler class available within the command group scope. These add a kernel function command to the current command group, and there can only be one kernel function command in each command group. In this example, we're calling one of the variants of the parallel for API. Now we're going to break down the different parts of this. The callable represents the kernel function itself, and this is the part which is compiled by the device compiler for the SYCL device that you're targeting. This can be either a lambda expression or a function object with a suitable function call operator. You may also notice that the parallel for function takes a template parameter. This is used to name the kernel function. This is important for pairing the kernel function across different host and device compilers. There are a number of different APIs for expressing different forms of parallelism, complexity, and functionality, depending on your use case. Each one takes the callable, but also takes some representation of the ND range. The callable also must take as a parameter a specific index type, which represents the current work item within the ND range's iteration space. And the type expected is relative to the API. In this case, we pass a range object, which represents the global range, and the callable takes an ID object, which represents the global ID within that range. These index types have a number of member functions for retrieving different information about the current iteration. There are three main ways to enqueue an ND range in SYCL. The first, in the top left there, is single task, which does as you might expect and invokes a kernel function exactly once. Single task doesn't take any range object, and the callable doesn't take any parameter. Next, in the bottom left, we have parallel for, which we've been looking at so far. There are a number of variants of parallel for, which we will cover in the next slide. Finally, we have hierarchical parallelism, which is split up into two APIs that are in the top right and bottom right, called parallel for workgroup and parallel for work item. Hierarchical parallelism represents the nested nature of SYCL workgroups and work items in a nesting of the two APIs. Parallel for workgroup is called first and is invoked per workgroup, and within that callable you can then call parallel for work item, which is invoked once per work item. For this lecture we're going to be focusing on parallel for, as this is the most common. There are three different variants of parallel for. The first takes a range object, which represents the global range, and the callable takes an ID, which represents the global ID within that range. In this variant, the local range is decided by the runtime. This is useful for when the kernel function doesn't need to know the size of the workgroup. The next takes a range object, again representing the global range, but in this case the callable takes an item object. The runtime still decides the local range, but the item object provides additional information. In addition to the global ID, it also provides the local ID, the global range, and the local range. This variant is useful for when you don't need to specify a specific local range, but the kernel function still needs to know what the local range is and the current work item's position in it. The final variant takes an ND range object, which represents both the global and local ranges, and the callable takes an ND item object. This variant is useful for when you need to specify the local range in order to ensure a specific workgroup size. All overloads of parallel for also take an optional ID object. This allows you to specify an offset. The offset, if used, will increment each index of the global range by the specified value in each dimension. So for example, if you have a one-dimensional range of 1024 and an offset of 512, then global IDs would now start at 512 rather than 0 and end at 1535. First, we're going to take a look at some of the rules that apply when defining kernel functions. Kernel functions can only be defined by a lambda expression or a function object. They can't be function pointers or std function objects. All variables captured in a lambda or stored in a function object must be by value, so they cannot be by reference. Kernel functions defined with a lambda expression must be named, and the name must be a forward declarable C++ type declared in a global scope. Lastly, kernel function names must follow ODR rules, which means you cannot have two kernels with the same name. This is important for using lambdas, as each lambda is unique and therefore needs a unique name. Now we're going to take a look at the restrictions which apply to kernel function code. These restrictions derive from limitations on what some hardware can do efficiently. Many heterogeneous architectures such as GPUs have less flexible control flow in order to provide higher parallelism and throughput. Some of these restrictions could potentially be loosened as heterogeneous architectures evolve in the future, so future iterations of SYCL may change. So you cannot do dynamic allocation in kernel functions, so memory must be allocated by the host application. You cannot do dynamic polymorphism in a kernel function, so virtual functions are not allowed. You also cannot call function pointers. Finally, you cannot have recursion, though template recursion is fine. Next, we're going to take a look at how to define kernel functions as function objects. So in all the examples we've looked at so far, we have used lambda expressions to define the kernel functions. Now we're going to look at how you can do this with a function object instead. A SYCL kernel function defined as a function object must store any variables such as accessors as member variables, and the function call operator must take the appropriate index type for the API you intend to pass the function object to. Remember, the member variables must always be stored by value. Here we have a full example of using a function object to define a SYCL kernel function. In the top right we have the function object we just defined, and on the left we have a simple vector add application now using the function object instead of a lambda expression. The parallel for is called as normal. However, before where we had a lambda expression, we now simply construct an instance of the function object type, initializing the accessors. Notice here that you now no longer need to pass a template parameter to name the kernel function. This is because the name of the function object type provides that name. Finally, we have the last topic in this lecture, precompiling SYCL kernel functions. This is useful for when you want to manually compile a kernel in order to have more control over how it is compiled. Generally, SYCL device compilers will produce binaries in an intermediate format such as SPEAR, SPEAR-V, or some other proprietary format. So when you enqueue a SYCL kernel function in your application, the SYCL runtime will often do just-in-time compilation to compile it down to the instruction set of the target device. This means that the first time you enqueue a kernel, it may take longer than subsequent enqueues. However, you can avoid this by pre-compiling your kernels. Precompiling kernels can also give you more control over how they're compiled, allowing you to specify specific flags or even linking other libraries. Here we have a simple application that we've seen before, and we're going to modify it to precompile the kernel in it. To do this, the first thing we have to do is to create a program object. Constructing a program object requires you to specify the context which you're compiling for. In this case, we're going to take the context from the queue that we enqueue the kernel to. Next, we need to compile the binary that contains the kernel. There are a few different ways that we can do this, but the simplest is to build it, which does both compilation and linking. We do this by calling the buildFromKernelType function, specifying the kernel name as a template parameter. You can optionally pass build options here as well, but in this case we don't provide any. If the kernel function was defined using a function object, we would use the function object type here. This has now done what the parallel for would have done implicitly. Now that the program is compiled, we have to retrieve the kernel itself. We do this by calling the getKernelMember function of the program object. Again, we specify the kernel name as a template parameter. This returns us a kernel object representing the specific kernel we want to enqueue. Finally, we call parallel for as normal, except now we pass in the kernel object as an additional parameter to instruct the runtime to use that instead of implicitly compiling one itself. We still need to define the kernel function so that the device compiler can compile it into an intermediate representation. This does feel a bit backwards in the flow of the application to be compiling the kernel before it's defined, however this is just an effect of the single source compilation. So this concludes the lecture on SYCL kernel functions. There should now be some time for us to answer any questions you might have on this. Welcome back. In this lecture we're going to be looking at how data is managed in SYCL applications. In this lecture we're going to cover the SYCL memory model, how to use buffers and accessors to manage data dependencies, how to access memory in different memory spaces, the different ways to access the data, how data dependencies can be used to control the execution order of your kernels, and finally how to synchronize data. First up, we're going to cover the SYCL memory model. In the last lecture we looked at the SYCL execution model and the composition of work items and workgroups. Here we're going to see how this relates to the hierarchy of different memory spaces available in SYCL devices. The fundamental component of execution was the work item, a single thread of execution. Now each work item can access a dedicated region of memory called private memory, and no work item can access the private memory of any other work item. Next up we had workgroups, a group of work items collected together. Each work item can also access a dedicated region of memory called local memory. Local memory is accessible to all work items of a workgroup. This makes it very useful for sharing partial results between work items. Again though, no work item can access the local memory of another workgroup to its own. Finally we had the ND range. Each work item can also access a single region of memory called global memory. Global memory is accessible to all work items in the ND range. It is also the only way to communicate data in and out of kernels, except for constants. Each work item can also access a region of global memory that is reserved as read-only called constant memory. Using constant memory can be an optimization for applications as it doesn't require cache since it's read-only. However, not all implementations provide a benefit from using this. Each memory region, private, local, and global, has a different size and access latencies, how to access memory in different memory spaces, the different ways to access the data, how data dependencies can be used to control the execution order of your kernels, and finally how to synchronize data. First up, we're going to cover the SYCL memory model. In the last lecture we looked at the SYCL execution model and the composition of work items and workgroups. Here we're going to see how this relates to the hierarchy of different memory spaces available in SYCL devices. The fundamental component of execution was the work item, a single thread of execution. Now each work item can access a dedicated region of memory called private memory, and no work item can access the private memory of any other work item. Next up we had workgroups, a group of work items collected together. Each work item can also access a dedicated region of memory called local memory. Local memory is accessible to all work items of a workgroup. This makes it very useful for sharing partial results between work items. Again though, no work item can access the local memory of another workgroup to its own. Finally we had the ND range. Each work item can also access a single region of memory called global memory. Global memory is accessible to all work items in the ND range. It is also the only way to communicate data in and out of kernels, except for constants. Each work item can also access a region of global memory that is reserved as read-only called constant memory. Using constant memory can be an optimization for applications as it doesn't require cache since it's read-only. However, not all implementations provide a benefit from using this. Each memory region, private, local, and global, has a different size and access latency. Private memory is the smallest, with local memory being larger and global memory being much larger still. And with global memory being the slowest to access, as it's often accessed across an off-chip connection, and local memory generally being quite a bit faster as it's usually on-chip, and private memory being faster still. Now that we've covered the memory model, we're going to take a look at how SYCL manages data using buffers and accessors. In SYCL, the storage and access of data is separated into buffers and accessors respectively. A buffer manages the data across the host application and one or more device, with the latest modified copy of the data being available in one of these locations at any given time. An accessor represents a request to access data on a particular device, in a particular memory space and for a particular kernel function. As well as describing requirements to access data, accessors are captured or stored in a kernel function and used to access the data once in the kernel. In order to achieve this, the host compiler and device compiler interpret accessors slightly differently. The host compiler interprets accessors as host application objects used to describe data dependencies to the runtime. And the device compiler interprets accessors as a wrapper over a pointer to the data that can be used very much like a regular pointer to access the data once in the kernel. There are many ways to construct a buffer that give you a range of options for managing data. Here we're going to focus on the most common of those. A buffer can be constructed with a pointer to host memory, i.e. memory allocated on the host application. For the lifetime of the buffer, this memory is managed by the buffer. So this means that modifying the original data on the host is undefined behavior, as the runtime needs to be able to freely move it between the host application and any devices that are accessing it. One important thing to note is that buffers are lazy. They won't allocate memory or copy anywhere until they're told to. This will only happen when the runtime knows where the buffer needs to be accessed. This is done by constructing an accessor to that buffer. There are a range of different types of accessors and ways to construct them. We're going to cover some of these later in this lecture. When an accessor is constructed, it is registered with a command group via the handler object. This connects the buffer being accessed to the way in which it's being accessed and where it's to be accessed. With this information, the runtime can schedule the command group in relation to others. Once the runtime scheduler selects that command group to execute, it must first satisfy its data dependencies. This usually means copying the data to the target device. However, if the latest modified copy of the data is already on the target device, it doesn't need to move. Sometimes the dependencies are on data already being written to by another kernel. In this case, it must wait for that kernel to complete before copying. Remember I said that buffers are lazy, so data will remain on a device even after the kernel is completed until it's requested elsewhere, or when a buffer is destroyed. When this happens, the buffer destructor will wait for the latest modified copy of the data to be copied back to the original pointer on the host application. Now we're going to look at a couple of different cases of using a buffer across different devices. If a buffer is accessed on one device and the latest modified copy of the data is on another device, then the data will be copied over. Now if the two devices are in the same context, for example both Intel, then the data will be copied directly from one to the other. However, if the devices are from different contexts, then the data will be copied via the host application. It's important to consider this as it could incur further overhead when copying between devices. Now we're going to take a look at the different kinds of accessors and how to use them. The accessor class has a number of template parameters which govern the various properties of how it accesses data. Firstly, there's the element type. This is the data type of the elements that are being accessed. This can be any standard layer and trivially copyable type. Next, there is the dimensionality, which can be 1, 2, 3, and even 0. Zero-dimensional accessors are a special case for accessing a single scalar value. Then there is the access mode, which is used to describe whether the accessor is reading and writing to the data. There are also discard variants of these, which describe an anti-dependency, explicitly specifying that the original data can be discarded. Next, there is the access targets, which specify the memory space that the memory is going to be accessed in. There are additional access targets for images that I've not described here, but I won't be covering these in this lecture. Finally, there is the placeholder parameter. This is an optional mode which allows certain accessors to be constructed outside of a command group and registered later. Let's look a bit closer at the access targets. Accessors with the access target's global buffer or constant buffer will allocate memory and copy to the global and constant memory spaces respectively. Accessors with these access targets must be constructed from a buffer. A useful shortcut for constructing a global or constant buffer accessor is provided by the getAccessMember function of the buffer class. The element type and dimensionality must always be the same as the buffer. Next, let's take a look at the access target host buffer. This provides immediate access to the data in the host application, so this means it must be constructed outside of a command group. Again, a shortcut to constructing a host buffer accessor is provided by the buffer class. Constructing a host buffer accessor can trigger synchronization and copy the latest modified copy of the data back to the host application. Also note that a host buffer accessor will block any other accessor from accessing the data until it's destroyed. Lastly, we have the local access target. Local accessors are a special case because they are not constructed from a buffer. Instead, you simply specify the type and the range of elements you want to allocate. However, local accessors allocate memory per workgroup, as they allocate memory in the local memory space. Local accessors are also only available for the duration of a kernel function. Now let's take a closer look at the access modes. The various access modes can be broken down into three main components. An access mode with read creates an accessor with read access to the data. An access mode with write creates an accessor with write access to the data. And this creates a dependency on any future accessor which accesses the same data. An access mode with discard creates an accessor that will discard the previous value of the data. This breaks a dependency on an accessor which are writing to the same data. Next, we're going to take a look at accessor resolution. If a command group has more than one accessor to the same data with conflicting access modes, they need to be resolved into one access mode in order to determine what the dependency is. The rules are, if you have both a read component and a write component, the result is the sum of those, so it will be a read-write access mode. Also, if you have an access mode with the discard component and one without, the result is one without, as that's the stronger guarantee. Within the kernel function, you still have multiple accessors, but the runtime dependency is resolved and the accessor is aliased to the same data. Here we have an example of this. We have two accessors here, in A and in B, which both access the same buffer, buff I. One is read and one is write. Both will point to a single allocation of global memory, but the command group will resolve these two accessors into a single dependency of read-write. Finally, we're going to take a look at ways in which you can access data, either in a kernel or on the host application, using accessors. There are a few different ways that you can access the data as represented by an accessor. Firstly, the subscript operator takes an ID. For dimensions larger than 1, the index is linearized using row major ordering. You can also use nested subscript operators when there's more than one dimension, so you have one subscript operator for each dimension. Finally, you can also retrieve a pointer to the underlying memory by calling getPointer. This returns an object of multipointer, which is a pointer wrapper class which knows the memory space the data is in. Here we have an example of using the subscript operator of the accessors to access elements of the memory, passing in an ID. Here we have another example doing the equivalent, but by retrieving the multipointer for each of the accessors and using the subscript operator on the multipointers to access the elements in memory. Here we use the ID's member function getLinearID to retrieve the linearized ID. Again, this is in row major ordering, just like the subscript operator of the accessor. So this concludes the lecture on managing data in SYCL. There should now be some time for us to answer any questions you may have on this.
Hi everyone, I hope you're still online. Unfortunately we had some technical hitches during today, but that's always going to be the case when you do stuff live. Presentations have finished now for today. There's still time to do the last exercise, and there'll be a bunch of people on the Slack channel for a while longer to help you with the exercise if you're doing that, or also to answer any questions that you still have. Don't forget to join us at the same time on Wednesday at 3 p.m. GMT, where we'll have some more interesting presentations from some different people as well, and also some live Q&A that's going to be happening with people from the SYCL working group. So you can submit your questions to the Slack channel either now or on the day, and we'll try to talk through some of those. So thanks for joining us, and look forward to hopefully seeing some of you again on Wednesday. Thank you.